So in this video, we're going to try to figure out what the derivative of the inverse trig functions are. But first, let's remember a little bit about inverse trig functions and how we find inverses in general. So we know that trig functions are not one-to-one, which means that we have to restrict their domains in order to get a function that has an inverse that is a function. So here's our graph of sine x, you can see. And you can see that if you just flip that in the line y equals x, you're going to get something that wraps around the y-axis, just as the original function sine x wraps around the x-axis. And so that won't give us, that's not a function. So we restrict the domain, so we just consider that part of the sine curve between negative pi over 2 and pi over 2. And in that case, we go from a y value of negative 1 to a y value of 1. So you can see our domain goes negative pi over 2 to pi over 2, and the range goes from negative 1 to 1. So to find the inverse, that means you swap the x and y, which means that the domain of the sine curve becomes the range of the inverse, and that the range of the original function becomes the domain of the inverse function. And you can see here is a graph of y equals inverse sine of x. Not terribly exciting, but that's what we have. Now notice that we say that y equals sine inverse of x, or otherwise known as y equals arcsine of x. These are interchangeable. It's a strictly increasing function. Right? It's always rising from left to right. Wait a second, see if I have any more space there. I'm going to do it down here. So for sine x, we know that if y is equal to the inverse sine of x, then if we take the sine of both sides, then the sine of inverse sine of x is going to just cancel, and we'll just get x. Now we're going to do a little implicit differentiation. So we're going to take the derivative of sine and get cosine of y times y prime. And on the other side, 1. Solving for y prime, that's going to be 1 over cosine of y. Now, let's see, remember that y is this inverse sine of x. That means, if you recall what that means, an inverse sine is the angle whose sine is x. So here I've drawn an angle whose opposite over hypotenuse is x over 1 is x. With a little bit of Pythagorean Theorem, whoops, there's my left hand touching it. So if I call that b for a moment, x squared plus b squared equals 1 squared. So b squared is 1 minus x squared. So b is going to be the square root of 1 minus x squared. So I'm going to call this the square root of 1 minus x squared. Now, this is 1 over the cosine of y. The cosine of y is the cosine of this angle, which is going to be adjacent over hypotenuse, which is going to be the square root of 1 minus the square root of x squared. This is what we're finding out. The derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. It's really surprising, I think, that you get something that looks nothing like sines or cosines at all, but more algebraic. Now, back to the derivative we call, hopefully you remember, strictly monotonic. So, since it is always increasing, we would expect its derivative to always be positive. And then we take a look at cosine x, and again we have to restrict the domain. For cosine, we go from 0 to pi, so that becomes its domain. We still get a range that goes from negative 1 to 1. So the inverse cosine, again, swaps those. So its domain is going to go from negative 1 to 1, and its range will go from 0 to pi. You can see that cosine x is always falling from left to right, so it is a strictly decreasing, or what we would call a strictly monotonic function. And because it's always decreasing, we would expect its derivative to always be negative. You have to remember that because we're going to figure these out in a moment. And in fact, let's do that. Let's pause for a moment here and find those derivatives. So let's look at, I'm going to look for a space here. I'm going to go back as inverse cosine. So if we are going to find that in a similar fashion, we're going to say, I'm going to use arc cosine rather, instead of the inverse notation, just so we get used to that as well. So I'm going to say, here is our function, y equals arc cosine of x. We'll take the cosine of both sides again. And so these on the left are going to cancel, and we'll get x is equal to cosine of y. We'll differentiate. Derivative of x is 1. The derivative of cosine y is negative sine of y times the derivative of the inside function, y prime. Solving for y prime, we're going to get negative 1 over the sine of y. Now let's go back and see what this means. Remember, an arc cosine of x means an angle whose cosine is x. Cosine is adjacent over hypotenuse, and so that's going to be x and 1. In a similar fashion, we're going to find this to be the square root of 1 minus x squared. So back to our derivative, we're going to get negative 1 over, and the sine of y, the sine of that angle, is opposite over hypotenuse. It is going to be the square root of 1 minus x squared. So what we're finding is the derivative of arc cosine of x is negative 1 over the square root of 1 minus x squared. Notice that it's going to always be negative because a square root is non-negative, and then a negative 1 over a non-negative is going to be negative. So let's see if we can put our wrap on this stuff here. We said that, am I back to, yep, so the domain and range of our inverse cosine. So our domain for the inverse cosine is going to be negative 1 to 1, and the range is going to be 0 to pi. And we've seen that its derivative is always going to be negative. So let's look at an inverse tangent. So here's our tangent curve, and we can see that since its domain goes negative pi over 2 to pi over 2, and actually it should actually be not including the endpoints because we've got vertical asymptotes at the endpoints, so it's not really defined there. So switching the domain and range, we're going to get our domain for our arc tangent or inverse tangent is going to be negative infinity to infinity, and this range is going to be from negative pi over 2 to pi over 2, but not including those. Okay, next panel. So notice that our inverse tangent is strictly increasing, which again we call a strictly monotonic function. And since it's always increasing, its derivative is always going to be positive. So let's find it. So we're going to say y is equal to the inverse tangent of x. We'll take the tangent of both sides, and taking the tangent of the inverse tangent is going to be just x. We'll differentiate that, and the derivative of tangent is secant squared of y times y prime equal to 1. So solving for y prime, to divide by secant squared, now remember secant squared is 1 over cosine squared, is to multiply by cosine squared of x. Now let's see what we've got. What do we mean by, cosine squared of y? That was a cosine, that's 1 over cosine squared of y. Now, y is the inverse tangent of x. That's an angle whose tangent is x. So doing a little Pythagorean theorem, we're going to get this is going to be 1 plus x squared. So our y prime is going to be cosine squared of x. Now cosine is adjacent over the hypotenuse, so that's going to be 1 over the square root of 1 plus x squared, which is going to be 1 over 1 plus x squared. No radical at all. So what we're saying is the derivative of arc tangent of x is 1 over 1 plus x squared. See how that's always going to be positive? So here is an arc cotangent. We see that graph over here. And notice that it's restricted to 0 to pi, and actually we won't include the endpoints there because it's not defined at those endpoints because those are going to be asymptotes. And its range is also going to be negative infinity to infinity. You can see then that the inverse cotangent will have a domain that goes from negative infinity to infinity and a range that goes from 0 to pi, but we have asymptotes at those places there, so it's never going to quite reach it. We can see that the derivative of inverse cotangent, because this is always decreasing, the derivative is always going to be negative. Now, let's see. And so I think we can see it. Let's see if we can just see the pattern, very much like what we saw in the other derivatives of trig functions. So our derivative, let me go red here. So our derivative of an inverse cotangent, so I'll say, I'm going to call it an arc cotangent of x. Now we saw that the derivative of an arctangent is 1 over 1 plus x squared, and so the derivative of an arc cotangent will be negative 1 over 1 plus x squared. The next one's the trickiest one. So we can see that a secant x is got kind of a crazy graph here, and it's not even showing up at all. But we can see the derivative of arcsecant of x. If you remember, let's put one up here real quick. Remember, the way we got secants back in our AP prep days was we would first graph a cosine curve, and then we would say where the cosine curve is equal to 0, we're going to get asymptotes. And we're going to share the high point and go up, and share the low point and go down. And so this is going to be our secant curve, but of course that's not a function, so we restrict our domain, and what we're going to do is just go from, we'll just keep, I went to green, let me get a different color up here. We're going to just keep this part of it in between here, like we did with the cosine. We're going to go from 0 to pi. And so when you just look at that piece of it, you can see this is going to be our graph of our inverse secant. So you can see here that since this is always increasing, that our derivative is always going to be positive for the inverse secant. I think I have room on the other page to derive this. So, yeah, this will work. So, let's take a look at our inverse secant. So, we're going to say that y is equal to the inverse secant of x. So, and remember, we know this thing's going to always be increasing. That's going to be important here at the end. I'm going to take the secant of both sides, and then to take the derivative, we're going to get secant y tangent y times y prime is equal to 1. Solving for y prime, we'll get 1 over secant y tangent y. Now over here we're going to draw our picture of our angle. This is the angle whose secant is x. So let's see. The angle whose cosine x would be adjacent over hypotenuse. So the angle whose secant is x is going to be hypotenuse over adjacent. Now with a little bit of Pythagorean Theorem, 1 squared plus b squared equals x squared. B squared is x squared minus 1. B is going to be the square root of x squared minus 1. So notice this is a little different than what we had in the arc sine and arc cosine because the order in this subtraction is different. Okay, so now let's see. We have 1 over, and the secant of y is going to be the reciprocal of the cosine of y. Cosine is 1 over x, so the secant will be x over 1. So that's going to make this be an x, right where this is. The tangent of y, the tangent of that is going to be opposite over hypotenuse, so that's going to be the square root of x squared minus 1. Now, we ponder this for a moment, but we remember that we said that the secant of the inverse secant was a strictly increasing function, which means its derivative must always be positive. Now, this radical is always going to be non-negative. The problem is, for different choices of x, that could be positive or negative. To ensure that it's always positive, we have to put it in absolute values. So this is where it gets kind of weird. But the derivative of an arc secant of x is 1 over the absolute value of the square root of x squared minus 1. Okay? Now, the domain of, now looking at the inverse cosecant. So here's part of our cosecant graph here, and our inverse cosecant is going to be here. Now we're going to restrict our domain from, it'll be an open interval, negative pi over 2 to positive pi over 2. Now the range is strange, kind of like it was with the secant. So absolute value of y greater than or equal to 1 says y is greater than or equal to 1, or y is less than or equal to negative 1. So there's an asymptote in here and another asymptote in there. There's a blank spot in our graph here where the cosecant doesn't exist, just like we saw with our secant. Okay, anyway, we can see that the domain and range, so we get a weird domain here. We could say our domain is absolute value of x greater than 1, greater than or equal to 1, or we could also note it's going to be x greater than or equal to 1, or x less than or equal to negative 1. So we get all the x stuff here and all the x stuff here, but there are no values of x between negative 1 and 1 that are used in the arc cosecant graph. And the range then is going to be between negative pi over 2 and positive pi over 2. Okay. And we see that it's always decreasing. So as you look at this, this is always going down, this is always going down. So the sign of the derivative is always going to be negative for the derivative of an inverse cosecant. And using what we saw before, the pattern, we're going to say the derivative of an arc cosecant of x is going to be a negative 1 over the absolute value of x times the square root of x squared minus 1. So just the negative of our derivative of arc secant. I'm going to summarize these in a moment. Now we have some weird identities. These are not easy to graph even on our calculator. So to graph an inverse secant, this is what we have to do. The reason for that, or where this comes from, is if we're trying to graph this, we know that we have 1 over cosine of x. Or let me do it this way. So we have our y equals inverse secant of x is what we want to graph. So if we take the secant of both sides, we get to here. That's supposed to be a secant, and we know that this is 1 over cosine of y. So we take the reciprocal of both sides of the equal sign. Cosine y is 1 over x, and then we take the inverse cosine of both sides. So this is actually how you graph on your calculator the inverse secant of x. Not an easy task to do. It's not, well, you just look at it and know. And these are tricky too, but you can just use those. It doesn't come up very often, but you can just use those. Let's see if we can do some of these problems down here. Can we evaluate the arc sine of negative a half? Now remember, this is an angle, so we want the angle whose sine is -1/2. So ignore the negative for a minute. The angle whose sine is 1/2 would be pi over 6. That's our reference angle. Now, to be negative, remember, the angles where sine is negative will lie in quadrants 3 and 4. But an inverse sine is only defined between -pi/2 and +pi/2. So that means that we cannot use that quadrant 3 angle. We must use the quadrant 4 angle, and we must use that negative angle. That's the only correct answer to that question, what is the arcsine of -1/2? These were tricky. The angle whose cosine is 0. So cosine is 0. Remember, if you think on your unit circle, cosine is going to be 0 at pi/2, 3pi/2, -pi/2, -3pi/2, so on. But an inverse cosine is only defined between 0 and pi. So the only correct answer is going to be pi/2. Now the arctangent of square root of 3, we can think of that as being sine over cosine, and that square root of 3 as coming from square root of 3/2 over 1/2. So the angle that makes tangent square root of 3 is the same angle that makes sine square root of 3/2 and cosine 1/2. And that angle is going to be pi/3. Now tangent is positive in quadrants 1 and 3, but an arctangent is defined in the same places that sine is, so only between -pi/2 and +pi/2. So our only correct answer is going to be pi/3. The inverse sine of the sine of 5 pi/4 is a bit of a trick question. You might think that, well, of course, they're inverses, they're going to cancel. The answer is going to be 5 pi/4. That would not be correct, because remember, an inverse sine is only defined between -pi/2 and pi/2. So at 5 pi/4, which is down over here, sine is going to be negative. But the negative values for sine have to come from quadrant 4. And so we have to get there by going through this angle. So this is going to actually be a -pi/4. Tricky, tricky. So number 5, the cosine inverse of the cosine of -pi/6. In a similar fashion, you might think that that is going to be -pi/6, but that would be incorrect, because the answer to an inverse cosine has to be an angle between 0 and pi. So we say, well, -pi/6 is down here. Cosine is positive in quadrant 4, so we need an angle that's positive that falls between 0 and pi. And so that is going to be a positive pi/6. Now, to solve this next one, we're going to take the tangent of both sides. So we'll take the tangent of the arctangent of 2x minus 3, and we'll get the tangent of pi/4. That will lead us to just the 2x minus 3. And if you remember, the tangent of pi/4 is sine pi/4 over cosine pi/4, but sine and cosine at pi/4 are both square root of 2/2, and anything divided by itself is 1. And then solving this equation is pretty routine. Okay, now I'm going to slide this up a little bit. Now we're going to use some right triangles to solve this. So an inverse sine is an angle. It's the angle whose sine is x. Whoops. So it's got to be opposite over hypotenuse. I didn't put that x in the right place. With a little Pythagorean theorem, we can find that this is going to be the square root of 1 minus x squared. So the cosine of this angle is going to be adjacent over the hypotenuse. It's going to be the square root of 1 minus x squared. And likewise, if we have an angle whose secant is square root of 5/2, that is the same angle whose cosine is 2 over square root of 5. So I'm going to draw an angle whose cosine is 2 over square root of 5. That's adjacent over hypotenuse with a little Pythagorean theorem. 2 squared plus, I'll call that a squared, is equal to square root of 5 squared. So a squared is 1, so a is 1. Now the tangent of that angle is going to be opposite over hypotenuse, or I'm sorry, opposite over adjacent is going to be 1 over 2. Okay, let's see if we can summarize what we know. Here's our derivatives of trig, inverse trig functions. Derivatives of inverse trig functions. And I'm going to do these in like we did with the derivatives of the trig functions, where you can see their relationships. So the derivative of an arc sine of x is 1 over the square root of 1 minus x squared. And the derivative of arc cosine of x is then going to be negative 1 over the square root of 1 minus x squared. The derivative of arc tangent of x is going to be 1 over 1 plus x squared. So the derivative of arc cotangent of x is a negative 1 over 1 plus x squared. And the derivative, these are the weird ones, of the arc secant of x is going to be 1 over the absolute value of x times the square root of x squared minus 1. Notice the different order in the subtractions. That is important. And the derivative of arc cosecant of x is negative 1 over the absolute value of x times the square root of x squared minus 1. Those two you must memorize and will be quizzed on regularly. Very good. Let me come back. We should probably do a chain rule with this as well. So if we did something like y equals the arc sine of 3x, then its derivative, so what we're going to get is du over the square root of 1 minus u squared. So the x's are replaced by u's. So du, the derivative of 3x, would be 3. We'll get the square root of 1 minus, and the quantity 3x squared is going to be a 9x squared. Okay? All right, let's do one more. Let's say f of x is going to be, say, arc tangent of x squared. Then f prime of x is going to be, we'll get du over 1 plus u squared. So the du is going to be the derivative of x squared, and then we'll get 1 plus x squared squared is x to the 4th. All right, there we go.